This is Physics 102B, Chapter 17, Part 2, starting with number 59. So we have an electromotive force of 12 volts and a current of 200 milliamperes. And the question is asking, assuming all the resistors are identical, what is each of the resistances? What we should first do is use Ohm's law to figure out what the equivalent resistance is. So equivalent resistance is voltage over current, and that gives 60 ohms. Now, the equivalent resistance means we're putting together these two in parallel, and then once you get those together in parallel, they're in series with R1. So let's figure out what an expression for the parallel resistors, that's R2 and R3. So for those two resistors that are in parallel, 1 over parallel resistance is 1 over R2 plus 1 over R3. And we're ditching subscripts at this point because all the resistors are equal, so we'll just say 1 over R plus 1 over R. So 1 over R parallel is 2 over R. And when you solve for R parallel, we get R over 2. Okay, that's the parallel portion. Now, the equivalent resistance for the circuit, we can just imagine that these two now are, they can be substituted with just RP, and RP is in series with R. So equivalent resistance is that R plus RP, which now I'm calling R over 2. And that gives us R plus R over 2 and 3/2 R. Which means the equivalent resistance for the entire circuit is 3/2 R. The question is asking what is R, so R is 2/3 of equivalent resistance. Now I put an asterisk right here because that's a result that we can use in the next problem, problem number 61. But when we do that, we find the resistance equals 2/3 of the equivalent resistance. Up above, we already found that the equivalent resistance is 60 ohms, so 2/3 of 60 ohms is 40 ohms. Now for number 61. Now we have, we're given for the same circuit diagram that each of the resistors is 50,000 ohms. We have a current of 10 to the negative 3 amperes. What is the electromotive force? I'm using the result from the previous problem that I had the asterisk by because it's the same circuit dealing with all three resistors being the same. So the result I had is equivalent resistance is 3/2 R, which means 3/2 times 50,000 ohms. So equivalent resistance is 75,000 ohms. Now when we use Ohm's law, current equals V over R. We want to solve for V, the electromotive force. So let's say V equals IR, and that gives us 10 to the negative 3rd amps times 75,000 ohms, and we get an electromotive force of 75 volts. Asks about the energy. Energy is power times time. Power is V squared over R. So energy is 24 volts squared divided by 150 ohms times the time of 60 seconds, and we get 230.4 joules. Number 66 asks to find the resistance. Let's use the same expression we used in 65. If power is volts squared divided by resistance, then resistance is volts squared divided by power. And plug in those numbers, 120 volts squared divided by 100 watts, and that gives 144 ohms. Number 69. power of 1750 watts, 120 volts, and question A asks about the current. So current is power divided by volts, and that gives 14.58 amperes. Question B asks about the energy. So energy is power times time. 1750, it's watts, but I wrote it out as joules per second so you can see how the units divide out. So 1750 joules per second times 600 seconds, and you get 1.05 times 10 to the 6th, or 1.05 megajoules. C, we want to know what the cost is for running it 10 minutes a day for 1 month. So we can say that energy is, remember, power times time. So 1750 watts times 10 minutes per day. And then the units, if you just stick with the units, now you have 17,500. And look at this, we had watts times minutes per day. So that's acceptable units, watts minute, watt minutes per day. Now we multiply by 30 days, the days will cancel out, and we're left with dimensions of watt minutes. 525,000 watt minutes. Now we want to convert this to the way the power company charges for energy, kilowatt hours. So we need to convert the watts into kilowatts and the minutes into hours. So we do our unit conversion, what I've done here in the green ink. We have, to get rid of watts, we have 1 kilowatt over 1,000 watts. To get rid of minutes, we have 1 hour over 60 minutes. What we're left with, minutes divide out, watts divide out, and we're left with kilowatt hours. And so we have 8.75 kilowatt hours. The electric company charges 8.75 kilowatt hours, 15 cents per kilowatt hour, so that's going to be $1.31.